A good day to all of you. This time we are starting a series named Fluid Uncovered. Here we will be unpacking the fundamentals of fluid. It will be a comprehensive exploration of fluid properties, classification and behavior. The content has been structured to reflect the core topics outlined in many of the UG courses. Myself, Professor Juned.N.Bhojawala, working as Assistant Professor in Government Engineering College, Dahod, Gujarat. Before starting of the lecture, I would like to thank our Principal Sir, Dr. K.B. Judal Sir, and my Head of Department, Dr. Paresha Baria Ma'am, for their unconditional support. So now let us start our series. Now what is fluid? We are using this word very commonly, fluid, but in reality a fluid is a substance that flows continuously when a shear force is applied. Even the force is very small. Like solids, if you apply somewhat force, a little bit shear force, it may remain on its place, but fluids cannot resist shear stress and they keep deforming until equilibrium is reached. In fluids, liquids as well as gases are part of fluids because they both show this flowing behavior. What are the examples of our day-to-day life? Water flowing in pipes and rivers, air moving as wind or through fans, oil flowing in engines, and blood flowing in human body. Why we have to study? Because we have to design water supply and drainage systems. We have to improve vehicles as well as aircraft performances. We have to understand ventilation systems and air conditioning. We have to analyze natural flows like wind and weather. So the key takeaway or the key idea is fluid always flows under shear, and its understanding helps us to solve real world engineering and day-to-day life problems. Now classification of fluids. The fluids are basically classified in four types, that is ideal fluid, real fluid, Newtonian fluid and non-Newtonian fluid. So the name itself suggests ideal fluids, means they are ideal. They have zero viscosity, they are incompressible, they are frictionless. But it is a theoretical concept. It is only used for simplifying the analysis. The real fluids, they exhibit all the properties like viscosity, compressibility and all the naturally occurring fluids. They belong to this category. Newtonian fluids. Newtonian fluids exhibit linear relationship between shear stress and rate of strain. Example water, air and most of the gases. Whereas non-Newtonian fluids exhibit non-linear shear stress relationships. Example blood, paints, polymer solutions. Now what is the continuum hypothesis? Though it is hypothesis, it is very much important to understand that. In this hypothesis, the fluids are treated as a continuous media and not as individual molecules. It is a continuous media, and this allows properties like density, pressure, velocity and temperature to be defined at every point in the fluid mechanics. Every point in the fluid, sorry. It makes us possible for use of differential equations for fluid flow analysis. It is valid when characteristic length of the flow is there. Mean free path of the molecules is available. Examples of valid cases are water flowing in a pipe, air flowing over aircraft wings, river and canal flows, and air ventilation in rooms. The limitations are high altitude gas flows and micro or nanoscale flows. So the key takeaway is when the flow size is much larger than the molecular spacing, fluids can be treated as a continuous media or a continuous medium. Now what are key properties of the fluid? So first and the foremost key property of the fluid is density. Density we all know is mass per unit volume. It is indicated by rho. It is measured in kilogram per m cube. It is very much critical for understanding concept of buoyancy and pressure calculation. Specific weight. Weight per unit volume. It is denoted by gamma. Gamma is equal to rho into G. It is measured in Newton per m cube. It is used for hydrostatic pressure analysis. Specific gravity. It is the ratio of fluid density to reference density. Means rho of the fluid to the rho of reference fluid. It is dimensionless in nature. For calculation purpose, reference is taken as water at 4 degrees centigrade. Specific volume. Volume per unit mass. It is 1 upon rho. It is measured in m cube upon kg. It is reciprocal of density as we can see from the mathematical expression. It is commonly used in thermodynamics. Now understanding viscosity. What is viscosity? Viscosity is resistance of fluid layer over another layer. Viscosity quantifies fluid resistance to flow and internal friction between fluid layers moving at different velocities. Viscosities are of two types: dynamic viscosity mu and kinematic viscosity nu. So dynamic viscosity relates shear stress to the velocity gradient. It is expressed as tau is equal to nu du by dy, where tau is the shear stress and du by dy, which is partial derivative, is velocity gradient. Its unit is Newton second per meter square or Pascal second. Kinematic viscosity nu, it is the ratio of dynamic viscosity to density. So nu is mu upon rho. It represents momentum diffusivity. Its units is meter square per second, commonly measured in strokes. One stroke is equal to 10 raised to minus 4 meter square per second. Now viscosity and temperature, what is the relation? So for liquid, viscosity decreases as temperature increases. Why? Because molecular bond weakens. It reduces resistance to flow. Example, honey flows easier when it is heated. That is the reason we have to timely change the engine oil, because of continuous heating and cooling it loses its viscosity. Whereas in gases, viscosity increases with the increasing in temperature. Higher the molecular activity, increases momentum transfer between the layers. And Sutherland's formula describes this relationship. So understanding this, temperature dependence is very much crucial for applications ranging from lubrication systems to atmospheric modeling. Now what is surface tension and capillarity? So surface tension arises from cohesive forces between molecules at a liquid gas interface. Measured in Newton per meter, it causes liquids to minimize the surface area. Capillarity, it is the rise or fall of a liquid in a narrow tubes due to balance between surface tension and gravitational forces. It is mathematically expressed as H is equal to 2 sigma cos theta upon rho gr, where theta is contact angle and r is tube radius. It is very much critical in porous media flow and microfluids. Vapor pressure. Vapor pressure is the pressure at which a liquid and its vapor exist in equilibrium at a given temperature. As temperature increases, vapor pressure rises exponentially following Clapeyron equation. When local pressure drops below the vapor pressure, cavitation occurs. It forms a vapor bubble. When this vapor bubble collapses, it damages pumps and propellers. This phenomenon limits the performance of hydraulic machinery. Compressibility. So compressibility measures how much a fluid's volume changes under pressure, quantified by bulk modulus K. So K is equal to minus of V dP by dV, which is again equal to rho dP by d rho by d rho. Liquids are nearly incompressible while gases are highly compressible. The Mach number indicates when the compressibility effects becomes important in gas flows. If Mach number is less than 0.3, incompressible flow assumption is valid. Mach number more than 0.3, compressibility affects significantly. If Mach number is greater than 1, supersonic flow with shock waves. So today we will be stopping here. Thank you.